afternoon. I don't think Wolfgang needs a special introduction because he's almost domestic. But let's remind us where he is now and where he came from. So you're now as a postdoc at the Friedrich Alexander University in Erlangen.
Yes.
Before that, he was for 2 years in Kochi, Vienna, and then before that, Parameter Institute, and before that, I'm not sure, but he did his PhD in USA.
Yes.
And finished in 2013. He also received the Einstein Prize for his work in loop quantum and gravitated spin forms in 2019. And also a special prize for his PhD. And is known for his work in loop quantum gravity, German quantum gravity, and classical gravity, and quantum foundations. And today we heard something about quantum geometry of the light.
Thank you, Czaslaw, for the very kind introduction, and it is really nice being back here in Vienna. And today I would like to speak about something that I have been thinking about for a long time, in fact, and wanted to do in different ways and experimenting different truncations, different techniques, and I think now I have some interesting result. Actually, there may be problem with my pointer, but that's not a problem. I think there's on. Maybe I should put on. Okay, so now it works. Okay, so the talk is about the quantum geometry of the light cone. And let's start out with a basic outline. So first I will give you just a very brief motivation of what I want to speak about. And then I speak about also the quantum theory. And then there seems to be something interesting happening, namely I can speak about the luminosity. So you know, for instance, a gravitational wave signal emits a certain energy per time. This is called in astronomy luminosity. But in if we take into account that there is h bar, g Newton, and c, the speed of light, we can build natural units. So out of the Planck, namely the Planck length, Planck units, and out of Planck mass and Planck time and speed of light, we can get a Planck power, Planck mass times c squared divided by Planck time. And it seems that in this quantization, the Planck power plays a certain role. And this seems exciting to investigate. But let's first go into the basic introduction. Yeah, that's better. Let me give you a basic motivation for what I'm doing. So in a quantum state represents the quantum analog of a classical state, of course. Classical states are points on phase space. In general relativity, phase space is space of initial data. And the initial data for gravity is the 3 metric on a Cauchy surface and the extrinsic curvature, which is basically the time derivative of the metric. This is like in mechanics, Q and Q dot are initial data for your particle motions. But then general relativity is different from mechanics because it is a gauge theory. And there is a gauge invariance, and this is diffeomorphism invariance. In fact, the initial data is not arbitrary. So not any 3 metric and extrinsic curvature will be compatible with the solution of the Einstein equations. You have to impose constraints, namely a scalar constraint and a vector constraint. And these are dual to vectors, vector fields in space-time that generate diffeomorphisms. In fact, generate diffeomorphisms only on shell if the constraints are satisfied. But what that means is that if we start out with some initial data that satisfies the constraints, then generate a solution to Einstein equations, but then choose a different hypersurface, we get new, which is related to the first one by a diffeomorphism, we get new initial data, but this new initial data will be just gauge equivalent to the original one. And so these states, let's say classical states on different Cauchy surfaces that are related by hypersurface deformations, they define the same physical state. And imposing these constraints is very difficult in quantum gravity, or the problem of quantum gravity is to make sense of the solution of these constraints, or to make sense of quantizing these constraints. But what this means intuitively is that so these different states are gauge equivalent, so we can, and the gauge equivalent data characterizes this gauge equivalence class. So one way to characterize this gauge equivalence class is to push this evolution to its natural extreme, namely when it hits the boundary of the future Cauchy development of this partial Cauchy surface. And this is a null surface. So instead of trying to imposing or solving at the quantum level these constraints that impose the Wheeler-de Witt equation, we can take now a different viewpoint where we characterize this gauge equivalent class of initial data, so different solutions or configurations of extrinsic curvature and 3 metric that satisfies the constraints, but different such solutions are gauge equivalent. How do we characterize this this complicated gauge equivalence class? Well, one way is to go to the null boundary, to the boundary of the future Cauchy development of these slices. And then the idea is to quantize gravity there. So to quantize the initial data on these null hypersurfaces. And the problem now simplifies, because now we have to quantize less constraints than before. It happens so that we don't have to evolve anymore back into the bulk, so to say, because the data at the null boundary already characterizes this entire gauge equivalence class. So we are left with less constraints. In fact, only diffeomorphisms that preserve this null hypersurface. And in that way, the problem simplifies. Yes, this is a good point to ask conceptual questions.
Would you also simplify if I chose like sigma 3 as a hypersurface? I say I will do everything on sigma 3.
But then you have to give a prescription what sigma 3 should be. For instance, it could be a surface of constant mean curvature, or a surface where the trace of the extrinsic curvature vanishes. So this is also a viewpoint which is being investigated, in fact. This is like the conformal method of solving the constraints. So my viewpoint is that, this seems to be supported by the evidence, that then the problem is still as complicated as before. While at this, the point is that at the null boundary, there's just way more structure available that we can use, and that we should take advantage of. Yes?
Just another question. In your picture, you have these surfaces that are spatially compact, right? They're not exactly Cauchy surfaces. Extend to infinity, and then they actually have a boundary.
That's right.
In your case, if you take into account true Cauchy surfaces, what do? You do it on like Scribe Plus or something?
So this is a very good, really very good point. But now my screen, I can answer it like this. So usually people would do precisely this. They would go to null infinity and quantize the geometry there. The problem with this viewpoint, in my opinion, is that there are now two limits that may no longer commute. There's a limit where, or you can first say, let's start out with the geometry. Let's first start out with partial Cauchy hypersurface, define the phase space there, and quantize it, and then within the quantum theory take the limit to infinity, to null infinity. But that may not commute with first taking the limit to null infinity and then quantizing. And this may be in fact related to certain infrared ambiguities, I believe, in quantum gravity that appear in the S-matrix approach. So there are two limits, and what I'm saying is it is possible to make sense of quantizing gravity in finite regions.
Okay. So complete linear approach, you take finite compact, no boundary, and you look how the degrees of freedom look inside of the domain of dependency.
So I consider the initial data on the null boundary, and then there will be a phase space, and the phase space can be quantized. But I will outline this step by step.
All right.
So in fact, this is precisely the viewpoint. We, instead of dealing with a complicated system of, for instance, an inspiral of two black holes that can then emit gravitational waves, and to study that, one would have to look at the spatial Cauchy hypersurface. The viewpoint is we look at physics away from the source, where we register null initial data at a null surface that where the radiative degrees of freedom can cross this null boundary. And then the procedure or the steps to follow to make this program work is to first find a useful parameterization or a neat parameterization of the geometric data at the null surface. Then you need to equip this space of geometries with a symplectic structure that it inherits from classical general relativity. And then you have to find a quantum representation of the algebra of observables. And what is really exciting is that this seems to bring together really different approaches. And I can speak here at the Institute of Quantum Optics and Quantum Information because there's a lot of interest in quantum reference frames, indefinite causal structures. But I could equally well have given this talk, in fact, at a conference that is just being organized close by at the Erwin Schrödinger Institute. So there's really something happening that different communities come closer together, which is exciting. Step one is to find a parameterization of the geometry. In here, so topologically, the null cone, ignoring caustics for a moment, is just a cylinder, okay? And in fact, I consider only an interval of the null surface. So what I'm interested in is to assign a phase space to a null boundary, but only to a portion of a null boundary that will actually extend. And then the basic strategy is, if I can make sense of the phase space and quantum geometry of one such strip, by gluing quantum states together, I can actually build an entire light cone geometry. So the first step is to just look at one such band of nulls at a portion of the null boundary that is itself bounded by two cuts, an initial cut and the final cut. And now the geometry, now this is a null surface, and relativists, we all know in relativity, this null surface boundary is generated by light rays. And then the geometry is determined by the metric. And if we take the pullback of the space-time metric to the null boundary, we get an intrinsic metric tensor on this three-dimensional manifold. But this is a degenerate metric. So it has a one degenerate null direction, which is, of course, the direction of the null rays themselves. Diagonalize this metric tensor. And since the geometry is two-dimensional, but there's one degenerate null direction, I only need two orthonormal frames, two directions, two co-dyad, so basically a co-dyad. And now any such co-dyad can be parameterized in the following way. We introduce an overall scale, a conformal factor, and then there are the shape degrees of freedom that are encoded into an overall SL2R holonomy. Pictorially, you can think what's going on here as follows. The null directions have zero length. There's no geometry along these generators. The entire metric is basically two-dimensional with one degenerate direction. Now, a two-dimensional metric determines the shape of triangles, let's say, no? And so to understand the degrees of freedom in this metric or in these orthonormal frames, we can think of these triangles. Now, the triangle will be characterized by its overall area, so which is encoded in the conformal factor omega, but also in shape degrees of freedom that tell you that, however, preserve the area. So these triangles should all have the same area, but different shapes. And going from here to there, you have an SL2R, and going down, you have a conformal factor. Okay, this encodes the geometry. This way, we can encode the geometry of the null cone by an overall conformal factor omega and an SL2R parallel transport. In fact, I call this holonomy or parallel transport because this matrix does in fact tell you how to parallel transport along these light rays. This 0 EM0, this is just a fiducial reference frame. Fiducial, if we think of the geometry of this null boundary as S2 cross R, so you take a S2 and you shine light out of this null surface, then this possible choice for this fiducial reference frame is just E1 is d theta, and E2 0 sine theta d phi. So a round metric on the two sphere. But determining a round metric, which would determine a round metric at the two sphere, but the physical metric is expressed relative to this reference, flat, round reference metric. But on top of that, we need to choose, what I want to choose is a choice of clock, a notion of time along this null rays. And there's no preferred choice available. You can choose whatever you like. And for reasons that become more obvious later on, the following choice is useful, where what you have here is if on the right-hand side you would have 0, this is what we call an affine parameter. This is the analog of proper time along the null rays. But I correct this by a term that is proportional to the expansion of the null rays. So this is a measure for how the area of this geometry, the area density, changes as we move forward in time. And furthermore, this clock I choose such that the initial and final cross-section, the initial and final cut, have just values plus minus 1. And this choice is always available. Now, this describes the geometry, a generic geometry of a null hypersurface. But now not any general geometry is consistent also with the Einstein equations. To impose the Einstein equations at the null boundary, so for the null boundary geometry to be consistent with the Einstein equations, you have to impose the Raychaudhuri equation and nothing else, which means you only have to deal with this one constraint. In addition to that, there's also a transport equation for this SL2R holonomy along this SL2R parallel transport along the null generators, where sigma is now the shear. If the shape of these triangles is conserved along the null generators, the shear is 0. If the shape of these triangles changes as we move forward in time, the shear will be non-zero, and it will encode, in fact, this is the effect of what gravitational radiation does. If gravitational radiation crosses the null boundary, it will affect the geometry by changing the shear degrees of freedom. So gravitational waves do this shearing. Yes?
The transport equation is also a consequence of Raychaudhuri, or?
This is on top of that. So for the Raychaudhuri equation, in the Raychaudhuri equation, with respect to this clock, turns into this simple second-order differential equation for the conformal factor, which is sourced by the shear degrees of freedom. And the shear degrees of freedom you read off by solving this equation, or by taking the time derivative of this SL2R holonomy. This defines the shear degrees of freedom. And then you insert the shear into this equation to solve it for the conformal factor.
And the equation comes from where? The transport equation? Is it like the usual?
Yeah. This is just the definition of the shear. The shear degrees of freedom that enter the Raychaudhuri equation derive from first derivatives of the metric. But the metric is now encoded into this SL2R holonomy. This is why first derivatives of the SL2R holonomy define the shear.
So in a sense, it's a change of variables.
It's just a change of variables, precisely. So the question is how to translate the original geometry into this SL2R and conformal factor. So this defines the geometry. This gives you the geometry in terms of the variables chosen, and it is not arbitrary. It has to satisfy certain constraints, and the constraints are given here. And notice that there is also U1. This is just because we have, by going to autonomous frames, we have a further gauge redundancy, which is basically which is nothing else than a rotation in the plane of these triangles, intuitively. So there's also U1. So there's a U1 degrees of freedom that rotate your frame fields. Then there's an SL2R that encodes the shape degrees of freedom. And then there's a conformal factor that determines the size of the metric at the null boundary, the overall scale. And so phi and sigma are fields on the null boundary, and J, X, and X bar are matrices, just the generators of SL2R. But it's not enough structure, a phase space, algebra of observables, to then speak about quantum theory. And so we need the symplectic structure derives from the action, or the Poisson brackets derive from the action. The action I use is just the usual GR action with a slight modification. A modification that does not change the equations of motion, but it affects the symplectic structure. And this appears only in d = 4 space-time dimensions, because in D equal 4 space-time dimensions, in the first order formalism, when you work with tetrads and connections, you have two curvature scalars from which you can build an action that is linear in the curvature, and this action gives you back the Einstein equations. And this additional coupling constant that now appears is akin, similar to the theta angle that appears in QCD. And at the classical level, this has no consequences at all. It just changes the way you think about phase space. It does not change your the solutions to your field equations, but it does have effects in quantum theory, and we will see how this will play out, in fact. And from the action, you can define the symplectic structure. And then you obtain a the symplectic structure, in mechanics, this is just P dq. This D is this bold D symbols. These are differentials in phase space to distinguish them from differentials on the manifold. That's other authors would just write delta for variation. What is important here is that the symplectic structure, we need it because this gives us at the quantum level the algebra of observables. And starting from the action we chose, so this gamma action that contains the so-called Barbero immersive parameter, we obtain the symplectic structure on this null strip. And this has now three terms. What are these three terms? Well, first of all, we observe that this is basically an symplectic structure for SL2R matrices, group elements, that, however, depend on, that are fields on the null boundary, that are fields on N. And what we also notice is that there are different contributions. There's one contribution coming from the boundary, from the cuts, from the two cross-sections that I introduced, the initial cut of the null boundary and the final cut of the null boundary. And what we see here is that the U1 part of the SL2R is canonically conjugate to the area density. And then there's the second line. These are somehow bulk degrees of freedom, or degrees of freedom that live along the null hypersurface. These are the radiative modes, and these are precisely these shear degrees of freedom. Don't wonder about this sub-index I. I will come to that in a moment. It's not that important. So the second line encodes the shear degrees of freedom. This SL2R matrix is canonically conjugate to an SL2R Lie algebra element. And the third line is the clock. So the clock, the time variable that we introduced, is canonically conjugate on phase space to the constraint. This is not so surprising. The constraint, after all, generates gauge symmetries. The gauge parameter is the time variable. So at the Hamiltonian level, the constraint generates shifts in the time variable. A few more technical remarks. So I introduced this index I here. This is just a kind of U1 interaction picture where I split off this U1 factor into addressing of these shear degrees of freedom. And this capital D here is a dressed field space derivative. It is the ordinary variation minus a diffeomorphism, but only a diffeomorphism along the null rays. So changing the clock. And also note that the Barbero immersive, this additional parameter, appears only in the corner term. And this is very typical to terms that you add, or this is typical to terms in the action that you can add, but do not change the field equations. They only generate terms, corner terms, that change your symplectic structure, but do not change the field equations. The whole thing looks very innocent in a way, but this is, remember that this is now highly nonlinear because there's a constraint. The constraint says that this term in the bracket vanishes. So you have to first solve this omega So given sigma and sigma bar as free data, you can solve this equation and then plug it into the second line. Okay, so omega will depend in a nonlinear, highly nonlinear way on the shear degrees of freedom and on additional initial data that you have to specify. The Raychaudhuri equation is with respect to this clock, it is a second order differential equation sourced by the shear degrees of freedom, a second order differential equation for the conformal factor. So to solve this equation, you have to give me the shear as free initial data along the null boundary, but you also have to give me initial data for omega, two initial data, either omega and omega dot, or just omega at the two cross sections. But these cross sections, the initial data for omega has now its own symplectic structure, which is good. This means that at the quantum level, everything becomes quantum. The shear degrees of freedom become quantum because there is a symplectic structure for them. But the corner data, the data at the cuts that determines the initial data at the two cross sections for solving the Raychaudhuri equation will also have its symplectic structure, so it can also be quantum. And this is something that can never be seen in the asymptotic quantization, because what happens asymptotically if we go to Scry? If we go to Scry, we send, what happens? We send the area to infinity, or we go to infinite distance from the source. So this two surface cuts, these two-dimensional spheres, let's say, they become infinitely large. They become the celestial sphere, in fact. That's why people speak about celestial holography. But the celestial sphere has infinite area. It is an infinite distance. But this is, of course, an approximation. We do not make observations at infinite distance from the source. In any realistic experiment, we are at finite distance. In fact, Scry may not even exist for generic initial data, or when we are in a situation with positive cosmological constant, there is no asymptotic boundary which is light-like. But all this still holds. So that is why this is also interesting. And yeah, so what happens if we go to an asymptotic boundary? Then we would send this observable at the classical level to infinity. But this is in conflict with the Heisenberg principle that you cannot send a classical quantity just naively to infinity before going to the quantum level. But now all of this is highly complicated, I said, or highly nonlinear, because omega depends on the shear and the initial data in a complicated way, because you have to solve this second order differential equation for arbitrary shear. So this seems, and then it appears in here, and inverting out of the symplectic potential, you have to compute the symplectic 2 form, invert it, and then find a quantum representation. But this is very difficult because everything is now nonlinear. All the nonlinearity of general relativity is now in here. But there is perhaps a way to do this systematically in the following way, namely to restrict ourselves to a specific class of null initial data, namely those where the profile of the free initial data follows the shape of a step function. And we know that any smooth function can be approximated to arbitrary precision by just very tiny, very short such step functions, short in this coordinate. And the idea is now to do this truncation and quantize each such pulse separately. And then what do we need to do to quantize an arbitrary profile? Well, we just take the tensor product. For each of these pulses, there will be now a Hilbert space. So if we want to quantize a more general profile, we would take the tensor product of many such Hilbert spaces and trace over the intermediate boundary modes or edge modes. And in this way, I claim one can construct a full nonlinear and non-perturbative quantization of gravity on the null cone. So far, I'm only looking at the single parts. Okay? But now, of course, everything simplifies, because now the pulse is only characterized no longer by infinitely many degrees of freedom, but only by finitely many degrees of freedom, namely the height of this, just by numbers, not fields, the height of this pulse. And if you now, and now the point is actually, sorry for jumping back, what I now introduce is a truncation. Namely, I restrict myself to configurations where the shear is constant, piecewise constant. But then this equation becomes simple. This is just a simple second order differential equation with constant frequency, no? Everyone can solve this. And here also, so if sigma has the U1 part you can split off, and then the shear is piecewise constant. If the shear is not piecewise constant, you solve this equation by a time-ordered exponential in U. This is like a Schrödinger equation with a Hamiltonian that is in general time-dependent. But so you need a time-ordered product. But if sigma is just constant, you can solve this immediately, constant with respect to U. And so both constraints, both equations simplify for piecewise constant data. And then you can solve these equations and plug them back into the symplectic structure. And then what you get is an algebra. Okay, so in fact, basically two harmonic oscillators and an SL2R. So here the A and A bar, B and B bar satisfy harmonic oscillator Poisson brackets, and then there is the symplectic structure for this is a Poisson algebra for the SL2R Lie algebra on this sphere. So theta and phi are our coordinates. And on top of this, there is a U1, there is an SL2R Lie algebra group element that satisfies these Poisson commutation relations. So where is all the non-linearity now? This seems quite easy. Well, it is hidden in the definition of the variables. The relationship between how these oscillators relate to the geometry is a bit menacing, perhaps. So the Heisenberg charges, A and B, Heisenberg operators, they are related to the area density at the future cross-section, the constant shear, cos and sine are hyperbolic cosine and hyperbolic sine, and some complicated phase. However, the area at the two cross-sections, the area density at the initial and final cross-section, they are just combinations of number operators. L in here is the U1 generator. So at the quantum level, it will have a discrete spectrum as well, which means that the area density, the area of the initial and final cross-section, where the pulse either starts or terminates, will have has now a quantum representation, and there's an operator that represents it at the quantum level, and it is basically a number operator. And the shear degrees of freedom, they are in these oscillators. There's one, if you re-express the constraints in these variables, you are left with one residual constraint, which is highly nonlinear in terms of these oscillators. However, has a simple structure. On the right-hand side, you just have number operators for your oscillators, A and A. So A and B just satisfy standard harmonic oscillator Poisson brackets. And C is an SL2R raising and lowering operator. So on the left-hand side, we have raising and lowering operators. On the right-hand side, we have only number operators. What that means is this is simply a recurrence relations that we can solve. And that is in a way then the end of the story. So this defines your physical states on the null, on a strip of the null boundary for piecewise constant initial data, radiative data. What is also very nice to see is that the constraint generates, so if we have in here we have basically, we have to deal with the quantum, with the representation theory at the quantum level of SL2R. The representation theory of SL2R is characterized by its Casimir. And now we can ask, what is the value of this Casimir? And how do we express it? Can we express it back into geometric observables, into the area densities at the two cross sections and the shear? And the expression that you get is this. And this constraint commutes, this Casimir commutes with your constraints, so it is an observable. So it has a physical meaning at the quantum level. And if the Casimir is, if the U1 generator wins, you are in the discrete series representations of SL2R. If the ladder operators win, you are in the continuous series representations. So there seems to be a transition happening between two representations, two quantum theories, or two regimes. And what does happen physically when this transition happens? And what you can now, this is in this slide, I now take this equation to infinity. So I can now say, instead of looking at such pulse at finite distance, what happens if we take, this is a classical, so of course now what follows now only works under a certain assumption, namely that this has a good semi-classical limit. But if the quantization exists and has a good semi-classical limit, then these observables represent just usual geometric data at the null surface boundary, and then we can take the prescription to infinity, evaluate or take a pulse of finite duration that intersects future null infinity. And what we then have to do is to relate the variables that we introduced to the standard ones that people use in the asymptotic quantization of general relativity. And then what you find actually is that the transition happens at a certain critical value of this shear. Okay, at which value? Well, it has the transition between the continuous series representations and the discrete series representations happens at the value of the shear, a critical value of the shear that is just order 1, where gamma appears, gamma is the immersive parameter. And if you now ask, well, these shear degrees of freedom at null infinity, they encode the radiated power. So to what power does this correspond? Then it corresponds precisely to the Planck power. So the transition between the continuous series representations and the discrete series representations happens at the critical luminosity, which is of the order of the Planck power. This is, of course, only this derivation assumes number of things. Most importantly, the validity of the semi-classical limit, such that, and if that is true, then we can take this equation to future null infinity and insert the and use just the standard fall off conditions that we know from classical relativity. And if we do that, for instance, what one needs to do is to find the relationship between the time variable that we introduced intrinsically on the null surface boundary and the asymptotic boundary, the asymptotic bonded time coordinate that we know, but know well from classical relativity. And delta U measures then the duration of the pulse with respect to bonded time, because with respect to the time variable that we introduced, this has just duration 2. It's just a coordinate, so you can take any value you want, but if you re-express it in this bonded time coordinates, it has a certain, this pulse has a certain duration, and this duration fixes the relationship between the two choices of time to leading order in the 1 upon r expansion, r being the radius, the distance from the source. And what is also interesting is, just as a side remark, that humanity has actually come close to observing such power. The Planck power, what is the Planck power? The Planck power is Planck mass c squared times Planck time. If you do the calculation, you can do this in any dimensions, you find something surprising, that in fact it is only in 4 space-time dimensions that the Planck power is independent of h bar. In higher dimensions, Planck power does not, in higher dimensions, Planck power vanishes in the h bar to 0 limit. In d equal 4 space-time dimensions, Planck power is independent of h bar. And that means that the Planck power can appear in classical general relativity. It is allowed to appear. And in fact, if we ask what is the, if we take the in-spiral of 2 black holes and ask what is the peak radiated power, then since L Planck, the Planck power appears at the classical level, it can appear also in classical equations. So we can have in d equal 4 space-time dimensions, it is L Planck is allowed to appear. So it is no surprise, therefore, that in 4 space-time dimensions, the peak luminosity will be of the order of the Planck power. In fact, what we have, when we observe the emission of gravitational waves, we are, we are 3 orders of magnitude below the Planck power. So these are the most luminous events that we know of. And the research that I presented to you today, in my opinion, suggests that it may be actually possible that there could be remnants of quantum gravity effects that leak into the classical theory, because the Planck power is close, is the critical power at which something happens in the quantum theory, namely a transition between discrete and continuous series representations. And with this, maybe I give you a brief summary. So what we have achieved is a non-perturbative quantization of impulsive null initial data. And the quantum geometry that we so found has a quantum representation of both the initial data for the Raychaudhuri equation that lives on this codimension 2 cuts in space-time, but it has also a quantum representation of the radiative data that can cross the null surface boundary. So this will be quantum, but the data that lives on these cuts will be quantum as well. And the prediction, for instance, is that the area of these cross sections is quantized. And this agrees, the spectrum in fact agrees with what we have in loop quantum gravity, that the area, so here I said that the area densities at the two cross sections is basically a number operator where the immersive parameter now shows up. And this is just what I said earlier, that by introducing the immersive parameter, what we add is what is deformed at the quantum level is what's happening at these cuts. So this has physical effects. Okay. If we turn on gamma, and then something seems to happen. I have only indications for that come from well, actually it's a bit stronger than that. But what I find is that if we are in the continuous series representations, then what happens is that this something else happens. I should tell you. So for the discrete series representations, these recurrence relations can be solved very easily. It turns out that you only need finitely many. These terminate at some point, and they terminate because of the representation theory of SL2R. That so C and C bar, they are like L plus minus for SU2, just that in SL2R it goes in the other way. There is a minimum magnetic quantum number, and the creation operators go up. And this minimum for the magnetic quantum number means that implies that these recurrence relations terminate with finitely many states. But for the continuous series representations, this doesn't happen, and you have to sum up infinitely many states in which the quantum numbers for A and B become infinitely large, at which point the shear degrees of freedom diverge, which then implies that you can create caustics. And this can be avoided when you are working with the discrete series representations. But for the continuous series representations, there seems to be a problem, which suggests, in fact, that the theory at Scry, at future null infinity, will be governed by the discrete series representations. And what I hope is, and what I want to explore, is that this can provide a new window into the quantum gravity phenomenology. That the emission, for instance, the emission spectrum of a gravitational wave, that there will be some fine structure of the emission spectrum of gravitational waves that will be governed by this immersive parameter that can show up then in physical. Have physical implications. Thank you.
Questions?
Thanks for the nice talk. The immersive parameter, are there any phenomenological constraints or anything else aside from what you presented? Like, are there some speculations it could be large so that the Planck luminosity would be closer to what is already observed or something like that?
Mm-hmm. In fact, the immersive parameter sets the fundamental scale in loop quantum gravity. It's just like here we have a transition happening for the luminosity. In quantum cosmology, for instance, what one finds is that there is a maximum energy density. given by the Planck energy density, and the relative, which then depends on the immersive parameter. But of course, there is a more trivial, more immediate result. In fact, if gamma cannot be arbitrarily large. If gamma goes to infinity, this transition goes to 0. But we have observed gravitational waves, so there is already a constraint on gamma from there.
Yeah. Thanks.
Just very
Yes.
curiosity, is the continuous representation above or below the Planck power?
Above.
Above. So below Planck power, you should have the discrete.
Yes. But there can be many, many states, you know, because it's not that just because of discrete series representations, they are not, an immediate concern could be that there are not enough states, that this would be in conflict with, that the Hilbert space is not large enough. But remember that there is also now a Hilbert space for this data at the corner, at the cuts, the two cuts. And what is what determines the size of this Hilbert space? Well, this Hilbert space is characterized by characterizes the area of the cross section. So if the area is very, very large, there are many, many states. So but it's true below the Planck. So what this analysis shows is that below the Planck power, the spectrum of the emitted power would be the spectrum of the power that such a pulse carries would be discrete.
You mentioned the representation for SL2. Is it only bounded below, or is it bounded above as well? Is it
No.
finitely then states?
Well, if you quantize SL2R, this is unbounded. But not all states are allowed because there is a constraint. A constraint that links the quantum numbers for the area to the quantum numbers for this SL2R.
Okay.
So, what you get is a recurrence relation that goes down. And so you start from some maximum state with some magnetic quantum number n, c, let's say, and then quantum numbers for the two oscillators, and then you go down, and then it stops.
I see. Interesting.
Any other question? Can I ask something more kind of phenomenological? So you said that this will induce that the surfaces of the cuts will have some fluctuations. Am I right?
Yeah.
This is just quantization on light cones. Has nothing to do with the light cone itself, a priori. I mean,
Okay.
I can imagine many different light cones, but every surface on this light cone should have this fluctuations. Am I right?
Mm-hmm.
Okay. Good. Now let's take the surface of a light cone. What would mean this for the light propagation speed? Would it mean it's uncertain, or it's
I don't. Yeah. So this, your question hints at something. I think.
I'm
And no. I want to continue. It hints at. Sorry. It hints at an implicit assumption that this program relies on, namely that it makes sense that it is sensible to speak about such surfaces at the quantum level, which relies also on the assumption that the speed of light is that there are no fluctuations of the speed of light. In that sense, that there is no that these surfaces can be sharp in a way. And now you may ask, is this perhaps in conflict? Or, well, I would say that one you could imagine coupling matter in here to this to gravity, no, and define then light propagation and like we would do it in an experiment operationally. So we measure, we want to check whether, for instance, we want to check whether the speed of light does not depend on the frequency. So we would have to add, we would have to set up an experiment and then ask, how does this experiment translate into this formalism, and do we get some deviations? This could very well be. I don't know, because this is a very difficult question. So this is not a priori assuming a light cone structure at the quantum level like that is not necessarily in conflict with observing deviations from the speed of light in physical experiments when you do when you use physical rods and clocks, because physical rods and clocks may add additional effects. But yeah.
So it's a question in classical, if you do some canonical research and you would use dimension of space, and then it's a question, are the equation of motion the same? This has first nothing to do with quantization, just with handling your systems and building models. And I always ask myself if such a discussion is existing in quantum things. If you can reduce dimensions or reduce your space where you quantize, if this is compatible with first quantizing and then reducing, this was it too.
Yeah. So yes, this the starting point is a truncation where along each light ray you only have finitely many degrees of freedom. Still, there are infinitely many degrees of freedom in the angular directions. In fact, I should have also mentioned that the phase space is in a way ultra-local in the angular directions. So different points at different light rays are all space-like separated and mutually commute. So the algebra in the angular directions is ultra-local. But this goes a bit away from your question. The question was about the symmetry reduction and mini superspace. So yes, I would say all physics at some point relies on a truncation. So we do, whenever we do, for instance, when we do quantum chromodynamics, we use a lattice to perhaps even define the theory. So all physics relies on some truncation. The question is then how to go back to the continuum, or how to go back to arbitrary initial data. If you do a mini superspace quantization, it is not that you can glue many universes and get approximate to arbitrarily good precision any other solution. No? This is kind of obvious. But here we're in a different situation. When we are using step functions, we can use to approximate to arbitrary good precision any smooth function with respect to the usual standard L2 inner product for the initial data. So we are so this is a different kind of truncation, I would say. One that is, of course, you lose smoothness, but otherwise you can, in the limit where you have infinitely many such pulses and you stack them together, you can still reach any point in phase space. In phase space for the radiative data.
Okay. I think we can conclude at that point. Thanks.
Thank you.